Thank you very much, Esteban, Professor Quijada. First of all, I would like to thank all the organization of the IMIL and obviously to pass my strong congratulations about the organization of the IMIL, because even in this extreme condition in which we are living with the pandemic, really you are able to organize an excellent and success Congress. So congratulations. Well, my talk today is has a little provocative title, playing with the joke of green chemistry and green chemistry, because obviously we all believe in the concept of green chemistry as an ideal that we like to go by our research in our lab. But the question is, we can to approach to one ideal chemistry, to a perfect chemistry, to a green chemistry. If we consider what's mean a perfect chemistry, a green chemistry is probably because we believe in dreams, in magic. Probably the magician is the best, the perfect chemistry, because we have a lot of tools for carrying out transformation of material. I will start with a little joke. While the magic is involved in chemistry, really the transformation of a frog to a princess is carried out by a catalytic tools like a kiss. So sometimes the best magic stick is a simple kiss. So how we can really carry out a perfect chemistry, or to approach to the perfect chemistry? Obviously, in my opinion, the magic stick more suitable are the catalysts, because catalysts and between all of them, biocatalysts, are able to transform, and some of them with the highest selectivity and the full transformation substrate into a product. So really it's a magic stick for chemistry. So we can transform. The problem is that how to carry out this transformation and the condition what we need. In this case, all chemical reaction similar to we have a case screw. We have tools to carry out this transformation. In this condition, enzyme, which is probably the core of our work in Murcia, are the catalysts that we have used. But we like to combine the specific and fantastic action of enzyme with other tools that we have in order to design process without no byproduct, with no emission, without no waste, and why not, if possible, to no purification. And if we are able to recover and to reuse all, really we will go near to the perfect chemistry and near to the green chemistry, and why not near to the magic. This could be a very good aims. To carry out additional to catalysts, when green chemistry was started, if we consider really catalysts are in the center, in the middle of all the rest of principles of green chemistry, because really the production of waste or the use of solvents that are not safer are additional component in reaction different to the catalyst. The core, in my opinion, is the transformation to be so selective, so specific, in order to avoid any waste in product. So when we are able to combine, to mix all the principles of the green chemistry and all together, really, we can go to a green chemistry. If we, in the same process system, we are able to involve the use of special solvent to avoid the waste, to have an economic atomic, to reduce derivative, etc. And so in this context, we are the weapon, the tools that we can use additional to catalyst. Obviously, we have to clear, and I will obviously talk about our experience in this kind of condition. The first one, all people know, are ion liquids. Ion liquids are practically exceptional, excellent, because are liquid formed only by ions, non-volatile, non-flammable, highly stable, excellent reaction medium for biocatalysts. The only one problem is that when the use of ionic liquid was started in chemistry, most paper related the use of ionic liquid, but do not provide a clear way to extract product. And obviously, some of them do not provide a clear approach for full recovery and reuse of this kind of ionic. For example, at the beginning of this kind of research, in the case of biocatalysts, then cyanide introduces into the ionic liquid solution with substrate, the transformation occurs, and it was very unknown. Also, even today, most usual to add some organic solvent not miscible with ionic liquid to provide an extraction, and so reuse and recover the ionic liquid in continuous flow. But it's not a green process, it's not a magic process, because we need to use organic solvent. And additional tools in green chemistry to carry out magic transformation are supercritical fluid. Supercritical fluid are a state of the matter in condition of pressure and temperature higher than the critical point. And so in this condition, mainly the supercritical CO2, because there is other solvent that can be used but have other constraints such as the price or the risk, for example, alkyne or ammoniac or xenon. There is the more usage CO2 because it's cheap and safe, have property a lot of interest, because additionally to the enhanced mass transport rate, because has the ability to behave like gases involving entry into the material and able to dissolve solid substrate and then to extract them, has like diffusivity and liquid-like densities. And we can tune the solvent properties as a function of the pressure and temperature and design continuous process. The only one problem in all of these advantages of the supercritical is that provoke enzyme activation. But it was I like very much to remember this classic paper of John Bernanke. He was and also a talk in this congress, because for me was key from the point of view, because she discovered the mutual immiscibility between ionic liquid and supercritical CO2. There is supercritical CO2 and ionic liquid formed by phase system, and the CO2 is able to enter into the ionic liquid phase and to dissolve and to extract compound, and so provide an interesting opportunity. So taking into account these tools, this weapon that we can work with supercritical fluid, ionic liquids, and catalysts and biocatalysts, the question is how we in Murcia we try to work toward a green chemistry. And obviously, by comparison, the combination of a lot of tools like enzyme and catalyst, supercritical fluid and ionic liquid, and now recently we have introduced another concept such as the deep eutotic solvent, but some kind of specific deep eutotic solvent, and the ultrasonic irradiation. Our aims in our lab is always to avoid as maximum the byproduct, don't provide air emission, no waste, to be able to directly release nearly pure product, and of course, to the full recovery and reuse of the real system. In fact, to be the more possible near to the magic process. I will show you now different example of process that we have working in this difficult way go to the green and green chemistry. Our first green approach involved the use of biphasic reactor based on ionic liquid and supercritical fluid. This was an interesting approach because we take a protein, an enzyme, and we suspend a suspension of the enzyme, free enzyme, the protein, directly into a liquid, more in concrete, ionic liquid non-miscible with water. This fact is most important because the ionic liquid miscible with water provoke water stripping and usually destroy the 3D structure of the enzyme. So we use ionic liquid non-miscible with water. And this suspension of enzyme, the ionic liquid, was absorbed into a support like slide. And this introduced into a reactor. And then this reactor was filled with an inlet flow of supercritical CO2 and another substrate. And directly we pass the flow and we recover here the product. The system, the core of the system is like this: as supercritical fluid and ionic liquid are non-miscible solvent, there is the preservation of the ionic liquid cell around the enzyme is guaranteed, and substrate is introduced by the supercritical fluid and product releases again by the supercritical fluid. Well, by this kind of reactor was our first approach to the green processes. We observed an excellent result because not only the enzyme was also able to catalyze the reaction. In this case was a reaction, simple reaction, the synthesis of butylbutyrate ester, a flavor. But the most important is to understand and to know what's happening with the enzyme. And we observed that the enzyme was stable. A lot of time, each point of the graph was 6 or 4 hours of duration. And so a lot of time, the enzyme was stable. When usually enzyme deactivating supercritical. But the most crazy was when we observed the activity at 100 condition, not usual for one enzyme, such as 100 degree and 150 bar in pressure, because we observed a very high activity. It was an enzyme, which is a protein, not usually, which don't work in environment different to water, was active in this condition. So we test really enzyme awake catalyst or not. We go to extreme conditions, such as, for example, now is fashion, the topic of Venus. Venus is a planet where in the atmosphere is a supercritical CO2 planet. We have 96% in CO2, 100 bar in pressure, and the temperature is 150 degrees. It is an ocean of CO2. Well, we place the enzyme in this design condition, and now we carry out a reaction more complicated, such as a kinetic resolution. So for the reaction, the enzyme must recognize one of the isomers of a racemic mixture and to catalyze selectively the esterification, the transesterification toward this isomer. Well, we can look here that each point corresponds to 4 hour operation, and so we can look, for example, 150 degrees of time practically unchanged level of activity, and even at 150, 20 hours of operation in this extreme condition, and really ionic liquid are exceptional because provide a specific shell around the enzyme, avoiding the inactivation. So ionic liquid open a lot of opportunity to design chemical process of industrial interest in condition outside the limit of life. So demonstrating that enzymes really are not wake catalysts. If we look at this reaction, obviously this reaction is a classical reaction where the enzyme recognizes, as I say, one of the isomer, and in these conditions we only obtain the 50% of the product because the other substrate obviously cannot transform it by the enzyme. But If we introduce a chemical catalyst, we carry out a dynamic kinetic resolution. And in this process, the coupling of the chemical catalyst with the enzyme, the enzymatic reaction can shift the equilibrium toward the formation of the disaster. And really, theoretically, we can arrive to the 100%. But this is not a new concept. This is a concept classically used in organic chemistry. Now I would like to show you which is the difference into the chemistry and the green chemistry, and why not the green chemistry? Because in chemistry, this is a classical organic chemistry reaction. We introduce reaction in mixture with one equivalent, three equivalent of the ester. In this case, the catalyst, the enzyme. Another catalyst, such as a ruthenium, is a soluble catalyst, homogeneous catalyst. The reaction occurs in therbutanol, 70 degree, 87 hours of reaction, and we really are able to obtain the specific kinetic resolution, dynamic kinetic resolution, which yield arrive to a very important result, such as 92%. Perfect. But when the reaction finishes, in the reaction media, we have all this compound. There is both the acetophenol, which is an intermediate, which is aided by the alpha, the alcohol result of the hydrolysis, the excess of the other acid donor, the chemical catalyst, the solvent. So it's a very complex, classical chemicals, but very complex reaction media. The activity in those two was high because we need to wait until 87 hours. It's a process discontinuous. The purification is no green, no cheap. This is a classical chemical. On the contrary, if we introduce in a reactor the enzyme coated with ionic liquid cell and a chemical catalyst like a zeolite coated also by an ionic liquid, the four catalyst particles are able to catalyze the kinetic resolution. The second one, the racemization, this mixture of solid particles introduced in the reactor. And now we can observe how by entering CO2, the racemic mixture entering the reactor like as a black box, and magically at the exit we obtain directly one of the isomer and the 100% of the racemic result. And is in CO2, the CO2 is evaporated, and we obtain the pure product directly. But not only this fact, also we can obtain this process continuously, many days. If we change the condition, the reaction, the suitability of the reaction change, decrease, increase, etc., and we recover also for the conversion, also for the non-terminescences. So it's really a process where we can very near to the magic process. But this is the idea? No, because this fact, a problem could be if this kind of ionic liquid could be leaked to the reactor. Well, for this fact, we have entry another approach, another tool, such as in cooperation with Santiago, Luis and Eduardo García Verdugo, two very high scientists and better friends. They are expert in provide support containing covalently attached ionic liquid into solid support. And this we have used for immobilization, to absorb enzyme in this kind of support. By using this approach, we have developed other processes. For example, this process, such as the synthesis of biodiesel. It's a reactor, simple, now where we mix vegetable oil, the methanol, and in this system, in supercritical condition, as both saturated and non-miscible, we introduce H1 by a HPLC pump, CO2, and we are able to provide directly biodiesel, pure biodiesel. Similarly, the problem, for example, was that in this case, the catalyst show a continuous deactivation. It was crazy. But at the end, low level of activity, we take the enzyme particle of ionic liquid covalently attached and the enzyme, and we wash with a little drop of terbutanol, and we recover all the activity. And then we start again the reaction, and we decrease the activity, we wash, and we recover that. And now, if we introduce in the reaction mixture a little drop of terbutanol, the activity was maintained. This is because in the reaction there is two products. One is the biodiesel, which is fully soluble in the supercritical fluid, but the other product is glycerol. Glycerol is not soluble in the supercritical fluid, and so glycerol is remaining absorbed into the catalyst, the biocatalyst particle, and so providing a continuous deactivation poisoning really of the catalyst, and so we obtain really an excellent. But really, this process, though this is really green and interesting scientifically, is not something interesting from the point of industrial point of view, because the production of biodiesel should be cheap because should fit car and no people, and so this is an interesting process from the scientific point of view, but not from the practical point of view. In fact, it is necessary to take into account that the production of biodiesel is no green. This is the classical way to produce biodiesel. Biodiesel, by mixing vegetable oil and methanol, are not miscible. Usually, people introduce catalysts like NaOH, KOH, the reaction strain condition, and obtain a biphasic system where the biodiesel and the glycerol. Well, really, this is no glycerol, because this is the true product where is obtained industrially. This is no glycerol. The biodiesel, after the processing, it is necessary to wash very much with water to have a product not able to damage the engine of car, and it's a process no green. It is necessary to consume very much water, and obviously this provoke a very high price. Obviously, in the market there is country in which the recovery and the wastewater treatment are not like in other countries, and so the price of biodiesel change too much. But it's not biodiesel probably could be an interesting green solvent, but probably I say, but really is not greenly produced. Enzyme can now aid this process, because enzyme, when the enzyme take contact with methanol, enzyme kaput, there are no activity of enzyme, become deactivate very quickly. So it's not really an interesting way to carry out this kind of reaction. How we can approach to solve this problem with our technology? So I will present you the second green approach in Murcia, such as the discovery of the sponges, so-called for us sponge-like ionic liquid. Really, I would like to say here a new, such as this is one of the example of serendipity, because I will say that one day in the lab I was taking to purchase some product, and I mistake. Really, I would like to purchase octyl methylimidazolium bistifimide. I mistake the code, and really I purchased the octadecyl methylimidazolium. And when he arrived to the lab, I say, "Oh, it's solid. What's happened?" This kind of ion liquid is something standard, solid, are based in very large alkyl side chain, and really the melting point are higher than room temperature. But why not? We can fuse this ionic liquid and to use it as liquid system. And we try. We try for a reaction, this kind of ionic liquid. The first example that we used ionic liquid was, this case was the synthesis of flame. Now we don't use classical vinyl ester or ester. We use directly the carboxylic acid and the alcohol directly, and to take two substrates obtained from natural resources, and to take the reaction directly and to form the ester. So this kind of ionic liquid solid will melt by heating. We add this substrate, we introduce the enzyme, and we observe, for example, in solvent fluid, obviously there is no activity because we are at as lead 6 molar in acid, and so there are conditions that usually deactivate the enzyme. By introducing a molecular sieve to the definitely, we improve a little, but it's really in this kind of ionic liquid in which we obtain a better, higher conversion, such as 100%. The reaction is fully shifted to the synthesis. But now the problem is what's happened, how we can extract the product and reduce the ionic liquid, because if we are not able to extract the product and to reduce the ionic liquid, really no ring, no chip, no obviously, no near to the dream and magic chemistry. The classically, we could use supercritical fluid. Why not? In fact, this kind of product are interesting from the point of view. Our product, for example, rated in the cosmetic market. Why not? Membrane process by for example, molecular distillation or evaporation, or the classical distillation, which is the process that usually all chemists do heat and to separate by the boiling point. In our case, we do on the contrary. We freeze. And so the reaction media, which is liquid, when we go to the room temperature and then we centrifugate, we observe a phenomenon really impressionant, such as the separation, the physical separation between the solid ionic liquid in the bottom and the liquid product in the top. And even if we introduce this kind of freezer reaction media into a filter, we fully retain the ionic liquid, and the product is released like a sponge, streaming sponge, and we obtain this kind of product. If we repeat in consecutive step this process, we can really reduce the amount of ionic liquid until the full disappearing in the product phase. So it's really a product like a magic, because we introduce an acid, an alcohol in a reaction media, we freeze the transformation, we freeze and we release, and we have the product, and we have the reaction media even suitable to carry out another process. And in this condition, we have carried out a lot of synthesis of, and we can observe in gram milliliter, the very high yield obtained. For the reuse, it's very, very simple to introduce, to mix with the ionic liquid, to introduce the enzyme, the reaction, etc., and then to separate just by freezing. And this process we obtain a very, very good suitability of this kind of ionic liquid with regard the activity, the stability of the enzyme temperature. So this future, which was published in chemistry and also in chemical engineering, because really has a boring, surprising or amazing result with regard to separation, process where combined reaction and separation. Now, how we can arrive to the biodiesel after knowing the advantage we provide. If we analyze the process, really the reaction, we can introduce the triolane, for example. We start with biodiesel, third generation biodiesel. Third generation biodiesel is more simple because we use a vegetable oil, simple, edible oil, simple, with a very interesting simple chromatogram where it's easy to study. And the enzyme, in this condition, is able to catalyze consecutively 3 tensile esterification reaction to provide the methylrate and the glycerol. This is by using this kind of ionic liquid and sponsorized ionic liquid. The most interesting is that this ionic liquid is solid, methanol and the vegetable oil are liquid but non-miscible, but when we mix, the system becomes monophasic and liquid at 60 degrees. And this fact is very, very interesting, because in this mixture, in which we have the ionic liquids, we have the oil and the methanol. This is the reaction media initially, and then there is no differences. We can follow the time course of the reaction and ready to observe how the enzyme runs very, very fast, providing the full transformation of the oil to biodiesel. Something which was dependent of is more or less logic, dependent with the alkyl chain length in the ionic liquid. For example, the burst reservoir obtained for the most hydrophobic ionic liquid, for the largest alkyl chain of the ionic liquid, and slightly reduced for this case, and not for the case of ionic liquid, which is liquid and not miscible with the oil. Well, in all these cases, we obtain really a very fast transformation of the vegetable oil with in biodiesel. But even more, when we observe the stability of the enzyme in this ionic liquid, really by incubation of the enzyme at 60 degrees with many 3 months, and there is no losing in enzyme activity. So this ionic liquid are really exceptional to stabilize enzyme. Now the question is again, if we are able to transform the oil, the vegetable oil, to the biodiesel by our magic stick, how we can separate and how we can do to obtain a really more really magic processes. And so what's very simple, directly, because in fact we have 2 products such as methylthreonate and glycerol in the reaction media, we do force the addition of water, hot water, in the reaction media. And the addition of hot water provides this layer of slurry, and then we cool, we centrifugate, and this is the reaction. The precipitate, the solid ionic liquid in the bottom, a middle phase of water containing the glycerol, and a top phase of pure, directly pure biodiesel. And so this is really a very, very interesting process to carry out, even at industrial scale, because the full ionic liquid is recovered, the biodiesel is pure, and really the glycerol is clear here, as it should be, and no dark, and as we have observed in the classical chemical process. So, and in this condition, the reuse of the system provides us, once again, we observe how the enzyme after cycle lose activity. But if we wash the enzyme with a little drop of terbutanol, once again to avoid the retention of glycerol between cycles, we obtain a profile of full level of activity. Only wash with a little drop of terbutanol, the immobilizes enzyme, and we recover the full activity of the enzyme. Obviously, we can do and work for second generation biodiesel by using a substrate waste cooking oil, and in this case it's clear, for example, the key role of water, because when we don't use water, really the separation is not too much good, and when using water, really the separation between the ionic liquid and the biofuel obtained are really good. But we can go even to a third generation biodiesel, and now by using the oil which are from microalgae. This is an additional problem, because microalgae are living system in which a cell wall, a strong cell wall, which is necessary to destroy. And ionic liquid at the beginning directly are not able to destroy and do not provide the structure of the oil. So in this protocol, we mix ionic liquid, a sponge-like ionic liquid, with a little drop of diamine chloride which is an ionic liquid that everybody knows, which is able to destroy the structure of cellulose. In this condition, by having this mixture of ionic liquid, obviously this ionic liquid it is necessary to be careful because can destroy the enzyme activity. But at this condition, undissolved mixes in the exposure like ionic liquid, the enzyme maintain the activity. So in this condition, we have a pre-treatment in which this microalgae cell are introduced in the mixture of ionic liquid. Then we heat at 150 degrees and destroy the cell. The exit of the oil dissolved into a liquid phase with filtrate, and then adding the enzyme and the methanol, the enzyme reaction, etc. And we can do it. And we observe, for example, the different phase until to obtain the biodiesel of third generation with an excellent operational stability, operational stability of the enzyme during the process. But this kind of ionic liquid spongyolite we have used also for process on the contrary, esterification, to carry out once again another important variable such as the synthesis, direct synthesis by esterification of monoacylglycerine. For example, by using glycerol directly with lauric acid. This is a compound very fashion now with the nutraceutical compound, and this is a really difficult reaction because one of the substrates are very hydrophilic, are liquid, are highly viscous. The other is solid, is hydrophobic. When the fission is also viscous, and the product is amphibic. We carry out this reaction in this ionic liquid, and when the carboxylic acid is much hydrophobic, like for example, when using oleic acid, we are able to attain monoolane, but we can use this classical C18 methylation bisulfimide ionic liquid. But for the middle length of the alkyl side chain, like the monolaurine, we need to use an anion such as BF4. And in this case, we can look here, for example, at the profile of the reaction. And obviously, we cannot write, because it's a reaction, a classic esterification, we don't write the same level of shifting of the reaction toward the synthesis, like in the case of flavor, but we are really arrive until 82% in conversion. For separation, for the case of the ionic liquid non-miscible with water, such as this kind of ionic liquid based in the bisulfimide ion, we can use the classical protocol where by adding water and cooling authentication. In this case, was more difficult because it was basically just directly by cooling, and in this case we use a solvent like limonene to provide the separation between the ionic liquid and the monoline. In another case, for example, more recently, is the synthesis of monoglyceride omega-3. Omega-3 monoglyceride, we're doing two different approaches. In one is a continuous way. Now we take fish oil directly, and like we have all this problem with glycerol, to have the mixture of the reaction glycerol, we choose here a derivative of glycerol, such as the sulketal. In this case, in a reaction, including the immobilization enzyme coated with ionic liquids, we introduce the fish oil, the sulketal, and the enzyme carry out the reaction. And then the sulketal derivative was entered in a second reactor to carry out the selective hydrolysis of this sulketal ring to provide the monoacylglycerine. For this case, we observe, for example, that the profile is much intense, but once again, we observe the decrease in the activity produced by the glycerol. The glycerol released by the fish oil, once again poisoning the immobilization enzyme. So by washing with terbutanol, we obtain an interesting recovery of the activity. Then, by using a little drop of terbutanol in the process, we obtain a profile. But obviously, terbutanol is something that I don't like. So we introduce another way to carry out the process, such as a discontinuous way. In this case, we do a first step in ionic liquid, classically by introducing the omega-3 oil from fish or linseed, sponge-like ionic liquid with reaction, and then we add water and we separate the salt-ketyl derivative of the fatty acid omega-3. And then we recover the fraction free of ionic liquid, and directly by a zeolite at a smooth condition, we are able to reach 2G fully conversion in omega-3 monoglyceride. Omega-3 monoglyceride are much interested now in nutraceutical because provide an interesting way to absorb this kind of omega-3 better than the case of thiazide, because it's not necessarily the action of the lipase for liver, and is directly absorbed into the intestine, this kind of compound. To explain all this result of sponge-like ionic liquid, we use what happened, the theory of my friends, good friend as better synthesis and better friend than synthesis, but it's an excellent synthesis, Jailton Dupont. Regarding the structures, if looking inside the structure of ionic liquid, really we are able to find a region with more hydrophobic polar compound or more hydrophilic, and so we are a different kind of domain inside the structure probably are the responsible of this behavior, exceptional behavior of ionic liquid sponge-like activity. In fact, we propose that the ionic liquid, the sponge-like ionic liquid in solid form, really are packed like something like that, where the large alkyl chain can interact like in an egg box system. And when we dissolve, for example, biodiesel inside, we remain more or less like this condition. And then when we freeze and centrifugate, we produce the circuit of the stream of the sponge like a sponge-like. The first approach, the first approach that uses what? Ionic liquid are very good, sponge-like ionic liquid are better, but no ionic liquid probably is the best one. In this case, it's to carry a reaction in solvent-free system. And what's happened when the substrates are liquid? This is a very interesting approach to synthesize a glycerol carbonate methacrylate, recently published in chemistry, to synthesize an intermediate very useful for the synthesis of non-isocyanate polyurethane. For this reaction, we have used the ionic liquid technology to have a supported ionic liquid phase covalently attached, and then the enzyme. And so to have a dual role of this kind of enzyme particle, because firstly, this catalyst is able to by the enzyme transform a vinyl ester into an ester of glycidol, and then the alkyl side chain and an ion of the seal of the ionic liquid to produce the cycle addition of CO2, the cycle addition to provide the corresponding carbonate. And so to have double transformation in one phase. This is a very, very interesting approach in which the system, one again, without no solvent, just introducing the reactive, the CO2 at 1 bar pressure, so we can use or take this kind of process like a process of product of CO2 recovery, because it's not necessary to have a bottle of CO2, it's a 1 bar pressure, and we obtain really a very excellent level of activity and conversion maintaining with time with cycle. So it's a very another approach. Another one is what's happened when solid substrate are able to form this. I talked about this, but we have no working this. We have working in condition in which when we mix substrate and this substrate are solid and this substrate are able to form this. And this fact was good when we work for the case of panthenol. Panthenol is a compound very interesting in care and cosmetical science. Pantene, everybody know Pantene. And now the Pantene is contain or panthenol or pantenyl ethyl ether or 3-pantenyl acetate. But there is no compound, there is no discovered, no provided in the market. Panthenol derivative monopantenyl monoacyl ether. There is no. The idea is to carry out directly the synthesis by esterification, the direct in solvent. In this condition, when we mix panthenol, a solid, with the carboxylic acid, for example, here is palmitic, here is lauric, and when we heat, then we obtain obviously the two phase, the different phase, and when we mix, we obtain this dipeutetic solvent, but based on the substrate. In this dipeutetic solvent, which only contain both panthenol and carboxylic acid, we introduce the enzyme, and really we obtain an excellent level of conversion to have pantenyl monolaurate. Obviously, this mixture would contain 80% pantenyl monolaurate, and the rest is panthenol and the fatty acid could directly be used for for a cream or for a product in cosmetic, because the cosmetic formula usually have mixture of different compounds, and this could be because there is any other thing. There is panthenol, there is the fatty acid, and also obviously the ester produced by the enzyme in this condition with an excellent obviously stability. But what happens, for example, when the solids are not able to form a base in the condition of use? In this, for example, is the synthesis, or last example, the synthesis of ester of xylitol with lauric acid. Both solid lauric acid, solid xylitol, and we, in this case, we have introduced, without no solvent, ultrasound. The system, this is an ultrasound, we can look here, where the distance with the ultrasound car is controlled, the water temperature, we work at this condition, and we can control the power, the energy, etc. The reaction is similar to carry out directly the ester, but at both hydroxyl group, primary hydroxyl group are similar. Probably you can also obtain the diacyl ester of xylitol. It's another compound usually employed for the preparation of cosmetics and food products. Well, when we try this kind of reaction media, is something interesting, because you observe, for example, at 40 degrees, at 40 degrees, both are solid. This could be start to fuse, but both xylitol are solid. We start slowly increase in the yield of the mono lauryl ester of xylitol. And here we have a maximum of the lauryl ester with then decrease. It should be occurred that the synthesized monoacyl ester could have a little job of surfactant role, providing the reaction. But if we reduce, for example, the intensity of the ultrasound, and at the same scale, 1250 grams of the reaction media, we observe practically the same result, but we observe how this maximum of the ethyl ester is shifted to a more larger reaction time. So something really the role of ultrasound here should be more related with the mixture, the sonication in irradiation for mass transfer phenomena. However, it's something curious when we increase doubling the size of the reaction and having the low intensity, you observe how the system run faster, and probably because all the reaction made able to mix is improved, and so we write an optimization system. So this is the xylitol ester provide and really can be directly used for this kind of cream. For example, this is a cream in which there is panthenol and xylitol. Why not with both cream obtaining with this kind of product? Well, it's something near to the magic, because placing two solid inside and just like the magic stick, and to obtain a product without no emission, no solvent, no waste, is something really very interesting. So with this example, last I would like to conclude that it's possible to carry out this kind of process. We have tools, and we need to combine all the tools, like your liquids, vertical fluid, and why not ultrasound, probably also the case of microwave and the condition of deep detection. But really, if is it possible, we need to work with this kind of process, really to provide new science in this case. But I would like to say that to find the perfect magic, sometimes you have to kiss a lot of frog before to find your place. So it's not easy, and it is necessary to try very much with this kind of. I would like to thank all people who are working with us from the beginning. So there are now Susana, Rocío, Antonio, Eduardo, Santiago, Ayrton, and all of you for your attention. I don't like to finish before to show you the excellent periodic table that we have in the fashion of our building, which is the bigger in the world. It's the bigger in the world, and was used as an icon in the last International Year of the Periodic Table. And obviously I invite all of you to visit Murcia, to come in here, not in July or August because it's too much hot, but I'm sure that you will enjoy your stay in Murcia. Thank you very much, all of you, for your attention, and I'm able to, if you have any question. Thank you.
Thank you very much, Professor Lozano, for this very wonderful presentation. A lot of approach you have shown here to the audience, and I think we have time for questions. You can raise your hand and you can ask directly Professor Lozano, or you can write down your question and I will read it for you. Well, in the meantime, I have a question. And the first experiment where you combine supercritical carbon dioxide as a media for the reactions, you use the supercritical carbon dioxide as a, so to say, phase, as a receiver of the product.
Yes.
Right. Yeah. What is the role of the thermodynamic there? Because there is a dissolution process there.
The role of the thermodynamic in the process.
Yeah.
I suppose that in other paper, we have studied the role of the kind of the ionic liquids, so as a function of the structure of ionic liquids, with the type of the ester. So we have used the synthesis of different ester, of different kind, different alkyl chain length, the ester, and the ionic liquid phase as a function of different alkyl chain length in the ionic liquid. And effectively, we have found some correlation where the efficiency of the product is better when for the extraction when there is lower affinity. As increases the affinity, obviously the extraction is more difficult. Effectively, all process and the transfer between the supercritical phase to the ionic liquid phase and on the contrary need the optimization of both. There is one ionic liquid for one substrate and for one operation condition, effectively.
Okay, thank you very much. We have time for questions. You can raise your hand.
Yes, I would like to ask one question, if I may.
Yeah.
Hi, Pedro, first of all.
Hi, Pablo, how are you?
Congratulations for your work and for your talk, because it has been a great talk. I was aware of some of the things that you were doing, but not all of them, and it's always a pleasure to hear what you are doing.
Thank you very much.
I got a question on the part of the glycerol that you get in the water media when you are working. Would there be a way to try to use this water and glycerol to work in fermentation and use it as a carbon source to make other chemicals? Because that would be a nice way to say, okay, you don't need to remove the water that you have in the system, which is costly in terms of the energy that you are going to put. You just take this crude thing that you get, and you try to make ethanol or whatever kind of chemical that you might think on that, and then it's a way to have two products in the same process.
It's an excellent suggestion, because in fact, as difference of the classical process where it's very dirty with the sodium, here is clean, and so really we can directly use it for fermentation, and why not to obtain other fuels or chemical that really is really to complete the sector effectively. So it's one proof again where the process have a true interest to be carried out a bigger scale. So yes, fully agree. Thank you.
Thank you.
Okay, one more question. Write it down in the chat. I will read for you, or you can ask directly. Okay, if there are no more questions, I would like to finalize this session saying thank you very much, Professor Lozano, for this wonderful talk and the opportunity to have you here in these webinars. It was a very nice presentation, and I would like to ask you if you can say some words to the Ibero-American community.
Okay, thank you very much, all of you, and once again, congratulations for the excellent organization of the IMIL, and I wish that the following session of the IMIL will be personally, presentially, and now with this horrible pandemic are occupying all of us. So would be a very good opportunity to maintain the relation. And I hope to see you personally again. Thank you very much.